Welcome to this explainer. Look, if you're studying Cambridge AS and A-level physics, you are in exactly the right place. Today, we're completely tossing out the dry textbook pages. We're going to uncover how the universe actually works, going from the invisible, tiny atomic realm all the way up to massive, real-world engineering. Let's decode Physics 9702 together, shall we?
But before we really get into building our understanding, think about this. You're in the exam hall scribbling down what you think is an absolutely perfect answer. And then, well, freeze frame. The examiner's red pen circles a fatal error. Believe it or not, 9 out of 10 students make a critical mistake when dealing with fundamental physics principles, and it quietly costs them that top band grade. And the crazy thing? It isn't that they don't know the vocabulary, it's that they completely fail to establish cause and effect. They just state a result without proving the actual physical mechanism that caused it. So I want to expose this mistake before you even have a chance to make it. Because honestly, once you see where this error creeps in, doing it the right way becomes almost impossible to forget.
Okay, let's really dive into this. There is a massive difference between a failing approach and a top-band approach. One way is just a scattered collection of facts. This happens when someone just drops isolated keywords onto the page, kind of hoping to magically trigger a mark. But contrast that with actually connecting cause and effect. This is exactly what examiners are demanding. They want a logical bridge between the raw data and the physical theory. You can't just say a material breaks, right? You have to explain the exact microscopic failure that led to that macroscopic snap. Building this cause and effect bridge, that is literally the secret to mastering the entire syllabus.
Section 1. Unlocking crystal symmetry, the foundation.
To truly grasp how to build that logical bridge we were just talking about, we have to start at the absolute foundation and zoom all the way into the atomic level. Because everything massive that we observe in real-world physics, like the way a bridge holds weight or the way a circuit conducts electricity, well, it all starts right here, deep inside the internal structure of the material. Crystal symmetry isn't just some boring geometry term. It's the physical internal arrangement, the packing density, and the bonding direction at the atomic level. Imagine millions of atoms locked together in a highly specific three-dimensional grid. That exact grid dictates a solid's macroscopic behavior and its tolerance for defects. If you push on a material, its crystal symmetry decides whether it bends gracefully, snaps violently, or maybe conducts a pulse of energy. The internal microscopic physics perfectly controls the external macroscopic reality.
And this is exactly how you safely secure your marks in the exam hall. You want to use a specific 4-stage framework. Step 1. Define the core idea. Step 2. Describe the microscopic mechanism, like what are the atoms or charge carriers actually doing? Step 3. Identify the measurable macroscopic consequence of that atomic action. And Step 4. Connect that consequence to a real-world application or device. If you lock this sequence of cause and effect into your brain, you will never get caught dropping a vague, scattered collection of facts again.
Section 2. Macroscopic physics in action. Let's do a deep dive.
Now that we've got our micro foundation built up, let's see how that tiny internal symmetry scales up into massive, measurable physics phenomena, the stuff you actually need to calculate on your exams. Think about how a solid transitions under stress. When you apply a load to a material, you are literally stretching those internal atomic bonds we just talked about. Now, if the bonds stretch and then just return to their original packing arrangement when you remove the load, that's elastic deformation. But if you push too hard, you permanently rearrange that crystal symmetry. You basically force the atoms to slip past one another into entirely new positions. That permanent structural change, that's what we call plastic deformation.
The precise boundary between those two realities is the elastic limit. It's the critical point of transition. But hey, remember our cause and effect rule? It's not just some arbitrary dot on a graph. It is the exact threshold where the microscopic crystal structure breaks down and can no longer recover. When you explain this in an exam, linking that macroscopic point of failure directly back to the microscopic atomic bonds is exactly what guarantees you those high-order analytical marks.
Let's pivot for a second and see how this builds into an entirely different realm of the syllabus: circular motion. Whether it's a car relying on friction to round a curve, a roller coaster cart right at the top of a loop, or even a planet held in orbit by gravity, there is always a physical resultant force acting perpendicular to the velocity, pulling the object toward the center. This is your centripetal force. And say, in the case of a mass being swung on a string, the structural reality of the string, its internal tensile strength and crystal symmetry. Well, it absolutely must be strong enough to provide that tension without exceeding its elastic limit and snapping.
Let's also see how these exact same principles literally save lives through medical imaging. Take X-ray shadow imaging and piezoelectric ultrasound generation. How do they actually work?
Well, it all comes down to the internal structural density of the material being scanned. Bone has a tightly packed crystal structure, right? It's incredibly dense, which means it highly attenuates or absorbs the X-ray photons. Soft tissue, on the other hand, is much less dense, allowing way more X-rays to pass right through. That difference in microscopic density is exactly what creates the macroscopic shadow you see on the film. With ultrasound, we use a water-based coupling jelly to match acoustic impedances. This ensures those high-frequency waves enter the body seamlessly rather than just bouncing right off the skin.
All of this perfectly highlights why mastering these concepts matters far beyond just passing a test. The technology that literally runs our modern world relies entirely on internal physics. Engineers design semiconductor wafers by meticulously controlling atomic defects. Aerospace engineers forge turbine blades with incredibly specific crystal alignments so they don't just shatter under immense thermal stress while you're sitting there eating peanuts at 30,000 feet. Structural alloys, high-end medical diagnostics, they all depend on the exact principles we're covering right now. This is the real-world application stage of your exam answers.
Section 3. The exam boss fight.
Knowing the real-world applications is really only half the battle. You can't just stroll into the Physics 9702 exam with a kind of vague understanding. You need a strict, methodical strategy to defeat the questions they're going to throw at you. Let's take a radioactive decay calculation, for example, where you need to relate the decay constant to the half-life. To solve these problems, you need to execute a 4-step attack pattern. First, master the concept and identify the underlying principle before you even look at the numbers. Second, precisely extract your evidence and data variables from whatever graphs or tables they give you. Third, use scientific reasoning to build a logical bridge between that data and your theory. And fourth, present your finalized answer using the precise terminology the examiner is hunting for. It's a calculated, highly methodical process.
So the crucial takeaway here is knowing exactly what the examiner is secretly trying to penalize you for. Let's go over the examiner's hit list. First, never, ever skip the method marks. Even if you punch the totally wrong number into your calculator, you can still get marks if your logical sequence of steps is visibly written out. Second, avoid generic, vague terminology like the plague. Third, match your response to the specific command word. If the question says describe, you tell them what is happening. But if it says explain, you absolutely must provide the physical reason why it's happening. And finally, always link your evidence back to the physical reality of the scenario. Seriously, don't fall into these hidden traps that cost unprepared students their grades.
Section 4. Final exam takeaways.
We have covered a massive amount of ground today. From the micro-world of atomic symmetry to the macro-world of circular dynamics and medical physics, all the way to some pretty intense exam room tactics. If you remember absolutely nothing else from this explainer, I really want you to remember this quote. A disciplined paragraph that connects cause and effect usually scores more strongly than a scattered collection of facts. True understanding will beat rote memorization every single time in Physics 9702. When you can see the invisible forces, when you understand that a snapping wire or an X-ray shadow is just the macroscopic result of a microscopic reality, well, you don't have to memorize 100 different rules. You just follow the logic.
So, I'm going to leave you with a bit of a provocative challenge. Can you answer the memory challenge questions strictly from memory right now? What changes inside the solid? What is observed outside? And where does it matter in technology? Test your memory triggers by answering that in the comments below. Proving you can bridge the micro to the macro is exactly how you guarantee your success. Also, let me know down in the comments which topic you want decoded next. Keep questioning the physical world around you, keep connecting that cause and effect, and I will see you in the next explainer.